All right, good afternoon. Let's start the lecture. Okay, so we'll continue on an multiple integrals here. Today we're going to start the new topic here, which is on triple integrals. Okay. Yeah. So we finished the double integral, and now we look at a triple integral, and then we'll look at some applications of triple integral. Okay. After we finish the triple integrals, then we'll go on and we'll look at integral in vector fields again. Okay. Okay, so first, let's look at the definition of a triple integral. And where is the triple integral from, basically? Okay. So, assume that we have a region D, okay, in 3D space. So basically, if you wanted to relate to a double integral, if you recall that in double integral, our integration is regarding a region R in xy plane, right? So now, what we're going to do here is we have a region, okay, D in 3D space. So it's basically, you consider it as a sort of a solid object here, okay? Yeah. At the same time, we have a function. Let's call that w equal to f of x, y, z. So it's a function of 3 variables now, okay? So at the same time, we have a function this, which is defined, okay? The keyword is this. Defined, okay, which is defined in region D. Okay, so what does this mean? Actually, when we do double integrals, we had a similar definition. We have a function f of x, y, that function 2 variables, which is defined in the region R given there, right? So when you see defined, basically, which means is if we pick any point inside this region D, okay, pick any point inside here. Let's say maybe you're picking points out of here. Okay, maybe this is point. This point is xi, yi, zi. Okay, and then if you plug this point, the actual coordinates of that point, into this function f, then there's a value, right, come out of this function f here. So that's what this means here. It's defined. So you're putting a value, you take a point from region D, and you put it into this function f, okay, and you will get a value out of this function f. Okay, that's what it means defined. Now, this is mathematically what we're saying here is math defined. But if I really want to use in physical meaning, so maybe this is a solid object, and this f here represents the density of this solid object. So what's the density? Basically, there's a non-constant density. At each point, you have a density value associated, right? So that's basically how you can see this function is defined within this region D. Okay. So, for example, f could be a density function, right? Could be density function. Okay. So now what we want is, right? The objective is we want to compute the integral, okay, of this given function over region D. Okay, so we want to compute this integral over this function. In other words, for example, if this is a density, and we want to get what's the total mass, right, of this 3D object D, represented by the region D at here. Okay, yeah. So we can start with a very similar process like the double integral. Basically, what we see is, okay, so let's take a small box around that point there. Okay, so very small box around that point xi, yi, zi. Okay, and there's a basically we represent that small box using a small volume, let's say delta Vi. Okay, now, assuming that the density at this location or within this small box is a constant. Okay, so the density at this location is capital F of xi, yi, zi, and is constant within this small box. Okay, then your the little mass, right, the delta mass of that small box is the density times the volume, right, times volume. Okay, so that's the mass of this small box here. And if you are looking for is the total mass, so consider we have n number of these kind of small boxes, basically separating this object D here, then the total, right, is approximately, I goes 1 up to n, okay, and then you add all these small masses up, right? Sum them up, and we get an approximated, basically, mass of this object D. Okay, yeah, so that's approximating process. So now if we let n goes to infinite, right? If we let n goes to infinite, then this is not going to be approximate anymore. This will be an exact total mass, okay, if n goes to infinite. So n goes to infinite, and what does that implicate? This delta V at here is the area, or is the volume of this box here. So basically, delta Vi is the box. The volume is what? Is the area, base area times the height. So basically, it's delta Xi, delta Yi, and delta Zi, right? So the three sides of the box multiply each other, and you get the small volume of the box. Okay. So when n goes to infinite, and this delta here, basically, they all when it goes to D here, right? Okay, they all go to the D. In other words, this delta V goes into so-called dV here, right? dV. Okay. So basically, our dV is dx, dy, and dz. Okay, that's what happens. And at the same time, the summation sign will become integral sign. But now, because we have how many variables? X, Y, Z. So instead of just one integral, we have 1, 2, 3, three integral signs there. So which is called triple integral. So essentially, that's where triple integral comes from. Okay, triple integral. Okay, what are we integrating? We're integrating this function f. Okay, over which region? Over this region, not R, over this region D, right? Defined at the top there. Okay, so I'll temporarily put the dv here, but you should know that dv is basically dx, dy, dz. Okay, that's triple integral. Okay, and the only difference from double integral, you have one more variable, you have one more integration process here to worry about. Okay, so now let's look at some simple one very basic one. Then I'll summarize a typical process or steps of doing triple integral, just like a double integral here. Okay. Now, if you look at this triple integral here, okay, look at this one. Now, if I say if this function equal to 1, okay, if this function equal to 1, then we get this guy, okay, we get this. And what does this give you? Exactly. So, basically, you remember everything, huh? If single integral dt give you t, or t squared give you t squared, and triple integral doesn't matter how many integrals you have here. If there's nothing at here, and there's just a d something at here, it's gonna give you back the something here. So what you have here now is basically you get the volume, right? You get the volume of this d, okay, of region D. Just like one assignment, how do you get the area of ellipse, right? So what do? You basically, you do R is ellipse, and dA, and you get the area of the ellipse, right? Area of R, okay? Yeah. So that's a very simple application of this one here, okay? Yeah. Now, the question, of course, is if this is a regular object, you can get the volume pretty easily. Just like a double integral, well, what we need to figure out is we need to figure out a computable way to basically evaluate this triple integral here. Okay, so the next subject essentially is how do we evaluate? Okay. How do we evaluate this triple integral? Now, like a double integral, we have talked about the two different coordinate system, Cartesian and polar, to evaluate the double integral. So same thing for triple integral. We actually have three different coordinate systems, Cartesian, cylindrical, and spherical coordinates. So the first, let's look at it. How do we evaluate the triple integral in Cartesian coordinates? Okay. So bear in mind that the integration doesn't matter how many integrals you have, how many, one single variable or double integral or triple or more than triple. And what you need is you need to scan through the region you're integrating with. Okay? If it's a single variable, you're scanning through A to B. Triple integral, scanning through the area R. Double integral area R. Triple integral, we're supposed to scan through this region D. All right, scan through them, but no redundancy though. So let's look at this one here. So I'm going to use a little bit of a generic picture here to illustrate the process. Okay, so let's just say I have a region D. Okay, more or less looking like this one here. It has a surface at the top and it has a surface at the bottom here. So there are two surfaces. Okay, and if you drop this region D or project this region D into XY plane, we'll get a so-called shadow. Let's say in this case we'll indicate that using an R and a here. All right? Yeah. Now the question is, as I mentioned, how do we scan through this region D? Okay, scan through it, but without redundancy. Okay, yeah. So like a triple integral, when you have just a region R, so what do? We said we draw. If y decided on dx first, I will draw a line in the direction of x first. I get this portion here, right? And then I sweep this line across this region, so then you cover every corner of it. Okay? Yeah. Now for this particular one here, let's do the same thing. Yeah, let's change it. So we have to basically, like this one, we have to determine on the order of integration first. Okay? Yeah. So first step. So usually the first step is you need to sketch this region D. If the question didn't give you this region D, to facilitate, to better understand and also find the limits, is to sketch it. Okay. Now this is a part of the job. Sometimes require you a little bit 3D visualizations, right? Yeah. Sketch the region D. If the question didn't give you what the region D looks like. And we'll come across some typical region Ds, okay, maybe bounded by planes, or maybe part of the spherical surface, maybe part of the cylindrical surface. Okay, so we'll look at different ones there. But you'll by the end of the next lecture, you will be able to sketch most of the very typical geometries. Okay. And second of all, is once you sketch region D now, you need to determine, okay, on this order, okay, of integration. Okay, so order of integration, just like a double integral, sometimes really matters. You actually, one example, I think one forgot in assignments or tutorial. If you do in one order, let's say dy dx, and you actually won't be able to get anything. But if you switch the order, then you will be able to do the integral, right? Yeah. So in this case here, this graph here, as you will learn, as you have more experience, and you will see that it's best to evaluate the dz first, okay? And it doesn't matter with dx, dy next, but it's better to evaluate the dz first. And then actually in this case, dy next and then dx, okay? So basically, this is the process of determining this. In my case, I'll see, let's see, for example, I'll see dz, dy, and then dx, okay, is the order. Okay, let's say I'll use this order to illustrate the process of scanning through the region D. Scanning through region D means you integrate over this region D. Okay, yeah. Okay, so if I wanted to integrate with the dz at here, okay, so what do we do? Then the next step is, okay, determine the limit. Okay, find limits for z, y, and x. Okay. Okay, so this is how you do. You'll feel much comfortable now, just like a double integral. So I'm trying to find the limits for the z variable. So what do? We start from a point inside the shadow of this region D. So probably I should see here. In the first step, actually, you're not just sketching the region D. More often is you also need to sketch, okay, the shadow, okay, or the projection of D in certain plane. And that actually, in certain plane, that's based on the order of integration. Okay, sketch the shadow of the D in certain plane. Okay, in certain plane. Now, here's what happens. If we're going to integrate dz first, okay, if we're integrating dz first, then this shadow or the projection of the D, we're going to project that into the xy plane. Okay, so let me put down here. Oops. So here's what happens. If this is the order here, then we sketch, okay, the projection of D in xy plane. Okay? Yeah. So you can think of the other order now. If you decided to integrate with respect to y first, then you're gonna have to look at the projection of the D in which plane now. If it's y first, the x plane. Okay? Yeah. That's very important, okay? Yeah. Okay, so this is what happens, just for example, maybe draw the D at here, and then we project that into the xy plane. We got this region, so-called region R, representing this shadow. Then for the determine the limits of Z, so what you do is starting from this, okay, starting from this region R, or the shadow, okay. Starting from the region R, the shadow, pick any point, okay? Pick any point. And yeah, where we go? Okay, so pick any point, you draw a line, okay, in the positive z axis. Okay, so that why do I start from anywhere inside R is because if you start from here and then you draw a line in the positive z-axis, then you're guaranteed that you will go through this region D, right? You'll go through region D here. Okay, so that's the steps that are here. Okay, so start from any point in the shadow of D, which is basically the region R that indicated in the picture. Okay, and draw a line, okay, in positive z-axis. Okay, in positive z-axis vertically. Okay, that's the step. And inevitably, as before we described, if you consider there is a guy walking along a line in the positive direction, you will come into contact with the region D with the first contact or the entry point, and second contact or the exit point. Okay, that makes sense? Yeah. Then, if this is the first contact, then the value, the z value of that first contact is z mean. And this is the second contact, then the z value for that location is z max. Is that good? Yeah. So essentially, what we're looking into is we want to get this line here. Okay, this line. That's the first sweep. You first sweep through this vertical line, you get a line, right? So basically, you covered the region D from here to here as a line. Okay. So first contact give you this z mean, and second contact give you this z max. Okay, so now you get a handle. Now I got this one straight line at here by the first sweep. Okay, yeah. Then the next step is, because we decided to integrate with respect to y next. So the next step is you draw a line. The next step actually is the same thing as a double integral. So you draw the line. You draw the line, okay, in the y-axis, positive y-axis, okay, and through this region R, okay, in the xy plane. So that's the next step. Okay, so and the next step is, okay, draw a line in positive y-axis, okay, in the positive y-axis through this region R, basically what I call is the shadow of this region D in xy plane. Okay, and the first contact, guess what? Give you this y mean, and second contact give you this y max. All right? Yeah. So let's come back here. Let's imagine, right? Visualize what happens when we're doing this sweeping, basically in the positive y-axis here, right? So they see. Remember, what happens is in the first step is you end up with this straight line here, this line segment, right? The line segment. And then when we're doing the second step of a sweeping, and what happens is second step sweeping is we're going from the positive, from this y along the y-axis to the positive y-axis direction. So basically you're sweeping this line through this region D, right, going through it and in the positive y-axis. So guess what should you have now? After this sweeping from here to here, then the first is a line segment. Then after the second sweep, what do we end up with? Yeah, it's a plane, right? And it's a plane actually more or less has to intersect this basically the object D at region D at here. Does that make sense? Right? So basically you get a segment, a section, a cross section there. Okay? You got a cross section. Remember I said again, what do? We're trying to sweep through the region D here. So that's not completely sweep through yet, right? So after the first two steps, we end up with a cross section. Okay? So that's the next step now. So we want to sweep through them all. So then the next step is you sweep, okay? You can sweep this line, let's call this line L at here, okay? Sweep this line L, okay, sweep this line L through across, use the words, let's say cross, across region R, okay, across this region R. So what does that mean is basically imagine we'll have the operation in here. So after the first step, you end up with this cross section here. And the last step is you're basically trying to sweep this cross section in the positive X or negative X, doesn't matter, basically sweep through, right? Sweep across the region R. Sweep across region R basically means you are creating this region D. Okay? Creating region D here. So, and that's basically the boundaries, okay, for R will give, okay, will give this X mean and X max. Okay, X mean, X max. So in this particular case, as you can see, one bound is over here, the other bound is here, and if this is the last integral variable, and it's guaranteed that this has to be a constant at here, right? It has to be constant. So that's it. So you see the three steps that are here. First the line, then cross section, and then sweep the cross section, you get the region D. Okay? Yeah. So every corner is covered and no redundancy. Okay. So if you follow these steps, you guaranteed you can get the limits right. So let's see if in my case sit here. Okay, for this particular case, what does that mean? What is that max? First contact is with the bottom surface, and second contact is with the top surface. So Z mean basically will be represented using this bottom surface, and Z max is going to be represented using this top surface at here. Okay? Yeah. So in other words, our Z mean, it will be the bottom surface, and the Z max will be the top surface. Okay? Yeah. And the Y limit, this is the first contact, this is the second contact. So the first contact is the bottom curve, and the second contact is the top curve. As this indicated, bottom G1, top is G2. So Y mean is G1 of X, and Y2 is G2 of X. Okay. And the X, right? The X mean is A, and X max is B. Okay, that's usually looking at the boundaries of this region R. Right? It's basically just one more step compared to double integral, right? Yeah. But in terms of the sweeping idea, is the same thing. So let's take a look at an example. Okay. Any questions? It's all good? All right. Yeah. Okay. So I'm gonna give you a region D, okay, in the shape like this. So okay, so we have a top, there's a plane at here, so x plus y plus z equal to 1. Okay, yeah. And what we want is, we want to find the volume, okay, sandwiched by the three sides of the plane at here, and this top plane x plus y plus z equal to 1. Okay, so we kind of call it tetrahedron, right? Yeah. So, looking for the volume. Okay, yeah. Okay, so looking for the volume of this tetrahedron here, and as I actually was deriving the double integral, what do we mean? How do we calculate volume? Volume basically, here's region D, here's dV, and that'll give you the volume here, right? Let's get the volume. Okay. Basically, in this particular case, the integrand at here is 1. Right? There's no function f of x, y at here. It kind of simplifies the situation. Right? So the practice at here is to find the limits properly, right, by going through the steps that we just illustrated shortly. Okay? Okay, so what do? We basically, remember the first step is to sketch, right? To sketch. But I guess I already sketched for you. But if the question is, can you find volume between sandwiched by the planes and this one here? I guess you need to draw this plane properly here, right? Yeah. So let me show you a very quick. If you're giving a plane x plus y plus z equal to 1, then how do I draw the plane actually? Here's a shortcut. You see, if I set z equal to 0, then what do I end up with? That's x plus y equal to 1, right? So when you set z equal to 0, what does that mean? Basically, this is a plane. You're looking for is, what's the intersection between this plane and an xy plane, okay? So basically, you should know that this is x plus y equal to 1, right? So it's equal to 1. And similarly, if you want to look for the intersection between this plane and this xz plane, then you set the y equal to 0. So that's x plus z equal to 1 for this portion. And of course, for this one, it's y plus z equal to 1. Okay? Yeah. So once you get the three sides, you basically get the plane, right? So that's that you can here do here, and then you can extend the three sides, to get an infinite plane if you want, right? Yeah. All right. So try to get a volume. Then the next step, right? So first step, sketch. And second step is order of the integral. Okay. The order integral sometimes doesn't matter. Okay. In this particular case, it really doesn't matter. So let's see what I want is just like in my example, I'm gonna do dz, dy, and dx. Okay. So if I determine on the order of the integral now, and what's the next step? The next step is to sketch what? To sketch the shadow or the projection of this region D in which plane? In this xy plane, right? Yeah, because you're integrating with z first. So in this particular case, you look at this one here. Where's my shadow? Here, right? It's this triangle. Okay, so sketch the shadow of D in xy plane. Okay, xy plane. Because that shadow or the projection in the xy plane will give you the x and y limits, or the y and x limits for the integral. Okay. So then the third step is to determine the limits. Okay. And the limits are for the z, for the y, and for the x. It's pretty simple in this case. So we are integrating with back to the z first. So what we do is we can pick a point inside this region, inside this shadow R here. Then we can draw basically a line in the positive z-axis direction, okay, across this region D. And that's what it looks like. You basically draw them across it, right? Cross it. And then you bump into this region D with the first contact point, and then exit with the second contact point. Okay. So in this particular case, the first contact point will give us the Z mean, which is 0. The second contact point is on the top plane at here, right? On the top plane. So that means the Z max should be 1 minus x minus y. Was that right? The top plane, see, this is the top plane here. This is the top plane. And second contact is always on this top plane. And that's, you express the top surface, basically, express the z in terms of the other two variables, x and y here. Okay? Yeah. So my limit for the z is 0 to y minus x minus y. And we're integrating with respect to the z first, right? And then dy and dx. Okay. Is that clear? Yeah? Okay, so first contact, second contact. And the next step is to draw a line in the positive y-axis direction. First contact is y mean, and second contact is y max, right? Is y max. Apparently y mean is 0, and y max falls onto this straight line x plus y equal to 1. So y max is 1 minus x. Okay, yeah. Question? No, okay. So 0 to 1 minus x. Okay. The last step, you sweep this bottom line here, sweep this bottom line across this shadow here. Okay? Find the boundary, the sandwiching this shadow. So where's the boundary? One bound is over here, and the other bound is over here, right? So this bound corresponds to x equal to 0. And this bound at here, that value is x equal to 1, right? It's 1. So your x limit is 0 to 1. Is that good? And that's a complete sweep of this region D. Okay? And as a matter of fact, even without doing this step, even if you're just calculating using high school geometry, how do you get the volume of this guy? Divided by 2? Is it divided by 2 or divided by 3? 3, right? Yeah. So the bottom error times the height and divided by 3, right? Yeah. And it's actually easier to calculate than this triple integral here. Okay? But anyway, let's try this triple integral here, okay? And the first integral is this portion. Okay? That's pretty simple. Let's just give you y minus x minus y dy and dx. Okay? I often find a lot of the time, okay, I'm not enforcing this, but when people come here and ask me a question, and I often find you guys don't like to use brackets. You know, when you're doing integrals, or integral a to b, y minus x minus y minus 4 minus whatever, and then dx at the end. So no integrals, no brackets, no brackets. Yeah, I actually admire you if you have a long expression, no brackets. You know, your brain needs to work really hard to keep organized here, right? But once you have a bracket, somebody will work for you, the bracket, right? Yeah, so I would encourage you, especially when you do programming, Yeah, you guys do programming, right? When you do programming, my habit doing programming is, and although I don't do that often anymore, the first step, I put a bracket first, and then I put my contents into the brackets. You know what I'm saying? Yeah. I don't type one side of brackets and then start typing and type another bracket. And guess what? You often forget the other bracket. So bracket helps you, huh? Yeah. Okay. So the inner integral here, you get this is the integral of y, so y minus xy half y squared bracket 0 to 1 minus x. Okay? And dx. And that's another thing. Don't forget a dx. Okay, so 0 to 1. So what do we have here? So y minus x to y. Y minus x to y. Y minus x to this y. So y minus x, y minus x, minus 1 half y minus x squared, and dx. And look at that, I forgot a bracket. Is that okay? Yeah. So then you're gonna simplify this bigger bracket, anything inside this bigger bracket here. Okay. So 0 to 1. Yeah. Yeah, because I know this is actually a tough job for some of you. Okay, you gotta basically do this though. So what do we end up with? Y minus x minus x minus x squared, and then here am I doing okay? And 1 half well, I guess I'm going to have to expand this now. This is 1 minus 2x plus x squared. Okay? Yeah. Yeah. Tell me if I'm making a mistake here, okay? So what do we have? Y minus 2x plus x squared minus 1 half plus x minus 1 half x squared. Simplification. 1 minus 1 half, 1 half. And negative 2x plus x is x. X squared minus this, 1 half x squared dx. Okay, yeah. Okay, so I think a lot of you probably will go from here is you can separate this three integrals into, the one integrals into 3 single ones, right? You can do that, no problem at all, okay? Yeah. And as a matter of fact, you can also do this. From here, a positive 1 half, yes? Oh yes, of course, positive, good. Yeah. So from here, you actually can do one more step of simplification. And this equal to 1 half 1 minus x bracket squared. Okay, this equal to this. So it actually depends on how you look at it. You can separate the integrals from here if you can, because if you come to this step here, and you actually have to use a simple substitution, basically let u equal to 1 minus x. Okay, yeah. So it depends on how comfortable you are, right? Yeah. But anyhow, we will end up with 1/6. Is that okay? Yeah. So if you like, you can try, what's the bottom area? The bottom area is 1 half times 1 times 1 is 1 half. And the height is, how much is 1, right? So, and then times 1/3. So it's 1/6. And that's what we get, right? Yeah. Okay, so you comfortable with the finding limits in Cartesian coordinates now? Yeah? Yeah. I'll give you an exercise that here you can try this one here, okay? Yeah. A little bit unconventional one here, but I'll let you try though. So, you don't need to calculate, but just practice finding the limits. Okay. So I'll draw the region D at here. Okay, so region D, there's a point here, so that point is 0, 1, 1. So this point is inside Y and the Z plane. And then there's another point, and this is a 1, 1, 0. So this is inside XY plane. Okay. And we will have one side of the region is this triangle here. Okay, that's one side of the region. And the other three sides is where you connect, okay, the two vertices with the origin at here. Okay. So basically, region D is below this plane, and between this plane and then plus the XY plane and the ZY plane here. Okay, so that's region D. Okay, the region D. Okay. It's a similar tetrahedron, right? It's still like a tetrahedron here. Okay, so now what I want you to do is, I want you to find the volume of this one. Okay, the volume of this. So volume. Okay, but I will designate the order instead of the dz, dy, dx. So this time, let's do the order of integral. Let's do this. Okay, let's do dy, dz, and dx. Okay, this is the order of integral. Okay, dy, dz, dx. And then, of course, what you need to do is, here is the triple integral. So dy, dz, and dx. So we're going to have to find the limits for the y, the limit for the z, and the limit for the x. Is that good? Okay. Yeah. So what you need to follow is the steps that we established just a few minutes ago. If I'm going to integrate with respect to y first, then the region is sketched. So what do we have to do first before you find in the limits? In which plane? Exactly, in the zx plane. So this is another skill you sort of have to be able to do it for simple regions. So for this one here, what do you think the shadow will look like? Triangle, right? Yeah. So basically, which triangle? This one, right? So let's just redraw the triangle here, or you can draw the projection over here. So this is the shadow, right? The shadow. Now, it's not just the sort of the sketch though. I think you will also need to do is, you need to basically label some of the important information that you're going to have to make use of, right? So what are the important things here? See, this point is projected over here. So in other words, at this location, what's the z value? It's 1, right? And this point projected here, and this is going to be 1 here too, right? Yeah. So then, in other words, for this side of this line here, it's a straight line. And in terms of the equation, which should be what? This one. There's no y. Y is 0. Exactly. X plus z equals 1, right? Yeah. So that's the line over there. Okay? Yeah. Okay, so now let's say we're ready to find the limits now, okay? Yeah. And what do we do? We're gonna draw because we're doing y limits, so we're gonna pick a point, okay, inside this shadow, then go in the positive y-axis direction. Okay, I'll go across this region D. Okay, go across this tetrahedron here. So first contact give us the y mean, and second contact give us the y max. So I guess one of them is pretty simple. It's y what? Y max, right? It has to be y max is going to be, what's y max? 1. So y mean is on this plane here. Well, I guess what you need to do is you have to come up with a plane equation for this portion here, right? The plane equation, okay? So let's hypothetically speaking, if here's the information you're giving, how do I get the plane equation? Yeah, cross product, right? Yeah, and you have many points on the plane. You have to you basically you have to form, let's say, a vector here, vector there, using 2 points here, and then do a cross product. Use that as normal vector, and use any point on the plane, and then plug into the plane equation to find the plane equation. Is that okay? Yeah, yeah. So, but more often, you do have a little bit a shortcut at it here. Okay? Yeah, you do have a shortcut here. So basically, because sometimes we look at it through the intersection of this plane with the plane on the side here. So first of all, what is the plane? What's the line equation at the bottom here? This line goes through origin and goes through 1, 1. So the bottom line here is, this line here is what? Y equal to x. And this line on the side here, this line here, goes through origin and goes through 1, 1. So this line here is z equal to y. So basically, this plane, right? This plane intersect this yz with z equal to y. Intersect xy with y equal to x. So you can actually summarize from this information. That gives you this y equal to x plus z. Why is that? So when you say y equal to x at here, which means what? Which means z equal to 0, right? Z equal to 0. So basically, see, if this is the plane, you let z equal to 0, you get what? Y equal to x. And you let x equal to 0, that's the intersection between the plane and this yz plane here. And then you get z equal to y. Okay? Was that good? So, I mean, if you're not confident, which is what I suggested, do the cross product, do the plane equation, right? That can't get anything wrong. Yeah. But normally, I will give you the plane equation, but just in case, okay? Yeah. Okay, so now can you tell me what's the y mean now? This is the plane, top plane at here. And the y mean should be x plus z. Right? Yeah. Once we find the y mean, y max, what we do is, the next step is we're doing the z variable next. So we draw a line, right, in the positive z-axis direction through this shadow or the projection, right, through the shadow projection. First contact gives you z mean. Second contact gives you z max. So z mean is 0, z max is 1 minus x. Last step, to sweep this line across the shadow here, find the minimum for the x mean and the maximum for the x. So 0 to 1, right? Is that clear? Yeah. So there are a couple of small skills that you need before you can find the proper limits, though, right? Yeah. Unless if the question is given, you can directly use the given information. Okay. So here's here's what I want you to do now. Okay. Can you change this? If I change the order, okay, I want you to exercise this. What's the integral limits if I want you to do this order? What's the order? So dz, dy, and dx. Okay, do this one here. And you can also try this one. Oh, let's just try this one. Yeah. Okay, let's just try this one. So dz first, then dy, then dx. 1 minute or two should be able to get that limits. So if Z first, then you have to find the shadow or the projection of this region in the XY plane, right? And then you draw an axis in the Z, positive Z axis across the region. First contact is Z mean, second contact is Z max. Okay, then you draw another line in the positive Y axis direction. And then X direction. Got it? Yeah. So here's the limits here, okay? dz, dy, dx, right? Yeah. So 0 to y minus x to 1, and 0 to 1. Okay, let me see who got it right. Not bad. Good. Yeah. Okay, so without calculation, what's the volume of this tetrahedron? Yeah. The same as answered before, right? Yeah. Okay. So you can try though, right? Okay. That's basically evaluating triple integral in Cartesian coordinates. There's no trick at all. Basically follow the 3 steps. Okay, you should be fine. And now let's look at the other way of evaluating triple integral. Okay, so let's look at evaluating triple integral in cylindrical coordinate. Okay. Just bear in mind is, you probably wondering, what's the hustle, with all these different coordinates? It's essentially you look at things from a different perspective. Okay, so transformation. Okay. So let's look at what's cylindrical coordinates. This is a Cartesian coordinate. Okay, we have a point, let's say P at here. Okay. In general, this P, right? It's basically can be represented using a set of x, y, z for its location. Now, what we can do is I'm going to project a P into the xy plane, and this is the x, basically this is the y, and this is the z. Okay. And then we connect the origin to this projected point at here. So remember, when you connect to here in the xy plane, we can call that an R, right? That's basically part of the polar coordinates. Okay. And then if you draw an angle always starting from x-axis to where this projected line is, okay? Essentially what you're projecting is you're projecting this vector OP, right? You're projecting vector OP into the xy plane at here. Then you get this here, so that's we define it as theta. And theta is always starting from x-axis, and theta is positive is counterclockwise, and theta is negative is clockwise. Okay? And a cylindrical coordinate essentially is a set of a number r, theta, z. Okay? So for cylindrical coordinate, it's r, theta, z. So in other words, you can say OP, there is a certain r, certain theta, certain z value, and that will give you basically the same location as the x, y, z. Is that good? Yeah. And of course, you can see now, what's the difference between this cylindrical and polar? Polar is in the 2D, right? And cylindrical is 3D. And the only difference is actually is r theta, that's the polar. And the z, that's the 3D component here, right? That's basically the difference. So if I want to relate this Cartesian and cylindrical coordinate together, so what do we have? The x equal to r cosine theta, and y equal to r sine theta, and this z is z, right? There's no change. Okay, so one set of coordinates x, y, z is mapped into another set of coordinates r theta y through this relationship right here. Is that clear? Yeah. Okay, so I'm not sure if you learned this in dynamics, but when I teach this cylindrical coordinate, polar coordinates, and later spherical coordinates, more often is I neglected one component. When we're talking about coordinate, what we're talking about is we're talking about coordinate system. Like this xy Cartesian, this is a coordinate system here, right? Now what's the coordinate system? You have three basically vectors, and we call it orthogonal. Those are three things perpendicular to each other, orthogonal to each other. Now, if I do the same thing here, basically what happens is, if this is the P at here, I can also construct a so-called cylindrical coordinate system. And to construct a cylindrical coordinate system is this. You draw a line in the direction of this r here. So that's the change. That's the change in the r direction. Just like you have a change, let's say, in the x direction here. Okay? So you can draw a line in this r direction change here. And then you can draw another vector perpendicular to this one, which basically represents is the direction of a change of what? Theta. Okay? Yeah. And the last one here you draw is basically the z here, perpendicular to the 2 at here. See, that thing, the three things that are here represent is this cylindrical coordinate system. Okay? Cylindrical coordinate system. So x, y, z Cartesian coordinates, when I'm writing, remember, vector, what do we use? We use I hat, j hat, and then what? And k hat, right? So basically we're representing each axis using a what? Using a unit vector. Now for cylindrical coordinates, basically, which is another coordinate system orthogonal to each other, we can use a similar notation. In most textbook, what they use is, they use this. They said this is a ER hat, and this is a E theta hat, unit vector. And this is what? EZ hat. And more often, to be consistent, instead of I hat, sometimes people write EX hat, and EY hat, and EZ hat. Okay? Yeah. So this is just kind of side things. I'm not going to test you anything here, but what you can bear in mind at here, this stage is you can construct completely different coordinate system. Okay? Yeah. This is x, y, z, and this is r theta z, right? So there are two complete different coordinate systems. Okay? That's basically the idea. And particularly when it comes to robotics application, image processing, when you have a different coordinate system, there is a technique called, how do I transform from one coordinate system to another coordinate system? Okay? Yeah, that's basically the next stage you will learn. Okay? Was that good? Yeah. Okay. So now we get the cylindrical coordinate system at here. Okay? What we can do is we need to figure out one thing is, okay, if I want to evaluate in this cylindrical coordinate, and what do we need to do? How do we transform from the previous Cartesian coordinate to this cylindrical coordinate, right? Yeah. See, previously this is the Cartesian coordinate fxz dv, right? That's the Cartesian coordinate. And now you're transforming it into the cylindrical. So if I do the cylindrical one, then what happens is this x, this y, this z. What do? We are going to replace the x with r cosine theta, and we're going to replace the y with r sine theta, and the z with the z. No change, right? So f r cos theta r sine theta and z. Okay, yeah. So technically, the d, we should call that d prime. Okay, but actually in this particular case, there's no basically deformation or change of shape in the d because of this change from x, y, z to cylindrical. So if you have a d in x, y, z, it stays as it is. Okay, basically. So you can still use a d here. Now the question here is basically, remember in the polar, so this is going to be dr, d theta, dz, that kind of a structure here. That's because we're using r theta z here, right? R theta z. So what should be put it at here? Right? What should be put it here? Okay? Yeah. Yes, it is r. But how do you know that's r then? You probably get that from the polar coordinates, right? But technically, we had one more variable here than the polar. So we actually, technically, what we should do is we should actually use, remember the last point in the previous lecture, what we call that what? The Jacobian, right? Determinant Jacobian to get this scalar factor. Okay? So let's try that, okay? Just to reinforce the Jacobian idea here. What's the Jacobian? So this is basically what we see. It's going to be the determinant of the Jacobian matrix there. And in this particular case, what's the Jacobian we're looking for? Jacobian, so is this matrix. So partial x over partial r, partial x over partial theta, and partial x over partial z, partial y over r, partial y over theta, partial y over z, and partial z over r, partial z over theta, partial z over z. Okay, so that's the Jacobian. Because you have basically you have three functions, x, y, z, three functions. And you form the Jacobian matrix like this, right? Like this. Okay. And if you calculate this, this is actually a pretty simple matrix. dx over dr, cosine theta. dx over d theta, negative r sine theta. And dx over dz is 0. dy over dr, sine. dy over d theta, r cosine. Did I miss the r? Oh yeah, I missed the r here, right? dx, no, I'm okay, yeah. And then 0. dz over r, 0. dz over theta, 0. dz over z is 1. Okay? Yeah. So it's a 3 by 3 matrix. And then you need the determinant of this one. Okay? Yeah. So determinant this one is 3 by 3, just like calculating the determinant of the cross product, right? Yeah, you should know that formula. So you will end up with r squared cosine theta squared plus r squared sine theta squared, which is r, oh, sorry, there's no square here, which is r here, okay, given as r. So r is a positive number, so we just plug it here. So that's basically the transformation from Cartesian to cylindrical. Is that clear? Yeah. So this is a more mathematical way here. You can also use a sort of approximation process, because you see, you know what this is. This is a dV, so that's the volume of a small patch, right? A small box. If I do this similar things in the cylindrical coordinate, so this portion at here should also be representing as a small volume in the cylindrical coordinates. All right. So I want you to check out the lecture notes in terms of this approach at here. Okay. So this is what you will see in the lecture notes. I think I'm gonna skip this portion. So this is basically you form a small box, okay, using the cylindrical coordinates r theta z, and calculate this volume of this small box right here. You will end up with that volume is r dr d theta dz. Okay? Yeah, so same thing. Is that good? Yeah. So that's basically that's it. That's what you're gonna C in terms of the cylindrical coordinates here, right? Yeah. Now, let me ask you a question at here now. So basically, it's a very short question. If I ask you is, if R equal to 2, okay, I say R equal to 2, what does this represent in 3D space? R equal to 2. So now you have to think in terms of cylindrical coordinates. So R equal to 2 meaning is a constant radius, right? If the xy plane R equal to 2 representing what? Circle. Now in 3D space, it's going to represent no, not sphere. Yeah, no. Yeah. You almost got me there. Yeah. See, the R represent the definition. R is from here to here. The R is a quantity within xy plane here. Okay, within the xy plane. So if R is a constant in xy plane, so it's a circle. Then in 3D, it's called cylinder, right? Does it have any top and bottom? It's a cylinder extending to the top and bottom infinitely there, right? Yeah. So this is a cylinder. How about theta equal to 45 degrees, for example? So what does that represent in 3D? It's a plane. Well, to be more precise, so where is theta? So this is theta here, right? 45. What kind of plane would you draw? Can I draw the plane? A pi is not is pi a plane? Well, I guess I would, what I'm saying is, I would draw like this, right? I'm not going to draw to the other side. You see what I'm saying, right? Because theta is 45 degree. If you have something over here, actually that theta is from here to here, right? That make sense? Yeah. So if this is just theta equal to 45 degree, it should refer to as it's like a half of the door there, basically, right? Yeah. Okay. Yeah. So yeah, just a simple exercise to think in terms of the different perspective, right? Using different coordinate system. Okay. So now let's do a quick exercise here. Okay. Maybe we're not. Yeah.
Does that mean R can't go negative?
No, R cannot go negative. That's a good point. So R is always a positive number here. Yeah. So because R is represent a distance from here to here, right? Yeah, that's positive. Yeah.
So theta just represents the direction of the plane?
Theta, okay. Here's how you interpret these things here, right? If I draw a line at here and I say, okay, theta is 45 degrees. What does it mean 45? You pick a point at here. A point at here. A point at here. What's the theta value corresponding to this point and that point? It's always what? 45 degrees, right? Now if I pick a point at here, basically on the top of here, okay? And what's the theta value corresponding to this point and this point? 45. But if I pick a point over here, it's not going to be 45 anymore, right? So that basically means theta equal to 45 degrees doesn't represent a point over here. Even if this point is more or less like in the plane as these 2 points here. That make sense? Yeah? So very good. Okay, so let's look at a quick example here and then we can call it a day. So usually by the tendency, I can tell whether you have an exam coming up or it's just finished exam. See, from my past experience, I normally have a significant reduction of a tendency right after the midterm exam, and it feels so relaxed. And let's skip a few classes. I'll tell you what, when you come back, brand new picture. Okay, so here's my region D, okay, described by two surfaces, z equal to x squared plus y squared, and z equal to 4 minus x squared minus y squared. Okay? And I want to compute the volume sandwiched by the two surfaces. So here is the exercise of drawing this region D. Let's draw it. Okay. We actually have seen the two kind of surfaces already. Okay. So z equal to x squared plus y squared. And remember what do we call that? We call that a paraboloid, right? Yeah. Okay, so it's a paraboloid here. And z equal to 4 minus x minus xy. It's pretty similar to x squared plus y squared. But this is 4 minus. Well, if you don't have the 4 here, if it's just z equal to negative x squared, negative y squared, it's basically a reflection of this paraboloid, which is pointing down, right? And then if you plus a 4 here, which means what? You basically shift up the bow by 4 units up. So in other words, let's see how much do we shift? We shift to the 4 units here, and then you draw another paraboloid, but it's pointing down. Okay? Yeah. And then basically it's like two bows on the top of each other, right? Yeah. Apparently there will be intersection between the two surfaces. And I can tell you it's going to be a circle, okay? And we'll figure out why it's a circle. Is that good? Yeah. Okay, so the question is, how do we get the volume of this one here? Now this is everything in terms of x and y. So I think you can try out the Cartesian coordinates. Okay? And I can tell you this is going to be a very ugly integral results if you use Cartesian coordinates. Okay? Yeah. And this is why we're going to try this as cylindrical coordinates. And since I'm running out of time, I'll try it out to the next lecture. Okay? Yeah. Any questions? All good? Yeah. Okay, so next Monday, I think it's next Monday there's no lecture, right? Just a second before no. Oh, sorry, not next week. It's a week after. So, okay. Next week we'll have the quiz. Okay, so don't forget to go to your tutorial section. Yeah.